3.1 Definition of derivative. Right, so derivative is nothing other than the slope of a function at a certain location. So if this is f of x, and here's location A, and we want to know the derivative, be the same as the slope of the tangent line like we had before. So there's a new symbol for it. I'm going to use f prime. Right? So you could read it as the slope of f, the slope of the function at A, will be defined as limit as x approaches A, f of x minus f of A over x minus A. We had this in 2.1 when we did the approximation and guessing. The only difference now is we've written a symbol, the limiting symbol as x approaches A, instead of just suggesting that x is getting close to A. So here's x, and up here again is x comma f of x, right? That's that point there. And like we had before, this point is a comma f of A. This distance is the numerator, f of x minus f of A. And this distance is the denominator, x minus A, as before. There's no difference whatsoever. And that this is the limiting value of the average rate of change. And it is called the instantaneous rate of change. Of the function at x equals A. So our average rate of change, once we apply this limit to it, and again, what is this limit doing? It's simply taking our secants, right? And it's making the secants converge more and more closely to acting like the tangent, right? So therefore the slope of the secant, which is represented by this expression here, right, the average rate of change, is getting closer and closer to being the slope of the tangent, right? Slope of the tangent is the slope of the curve, right? So average rates of change become an instantaneous rate of change, right? Happening at one single point, not between 2 points. Become the instantaneous rate of change, which is the slope of this green line. Now, so this is our derivative. Derivative of f of x at x equals A. Okay? There's another way to represent this. If we make x minus A equal to h, right? So this distance here, we will give a new labeling to. We'll call it h. Okay? So if x minus a is described by this letter h, then it's pretty clear that h approaches 0 as x approaches a. Right? Because if x is approaching a, then this difference here is certainly approaching 0. Right? H should be approaching 0. It's pretty clear from the picture anyway, if x is heading towards a, right? As we move down the curve here and create more and more secant lines, which are closer approximations to the green tangent line, certainly the distance between them is closing down to 0. That's all this is saying here. But it gives us an important way, a useful way to write the derivative definition. And that is f prime of a equals the limit as x approaches a is the same as saying the limit as h approaches 0. And if x minus a is h, then x, of course, right? If x minus a is h, then you could simply switch sides. You could move a over here, and you would also have that x equals a plus h. Right? So we can replace the x's in here, in this expression for the derivative, with a plus h. So you would have f of a plus h minus f of a. We didn't do anything to the second term of that difference. Over, well, if x is a plus h, well, a plus h minus a is just down to h. And this is perhaps the more common way you see this definition written. And it is the form I use for almost every problem that I do.